So this is Julie, and I just want to tell everyone that I got the PowerPoint, and my side is ready to play PowerPoint for the professor, Barbara Liskov.
Okay, I think it's time, so perhaps we can start now. Hello, everyone. As the General Chair of ISSTA 2020, and on behalf of the Program Chair and the rest of the organizing committee, it is our great honor and pleasure to welcome you to ISSTA, the International Symposium on Software Testing and Analysis. This is the 29th ISSTA meeting and the first virtual meeting. Our original plan was to meet in Los Angeles, California, United States, but due to the unfortunate pandemic situation, we had to cancel that plan. Our team has put in a lot of hard work to make sure the virtual conference is as successful as possible. In addition to a high-quality conference program, we also collected some nice photos of LA and Hollywood, which we hope you'll also enjoy. Next. I would like to acknowledge the outstanding work done by the organizing committee. First and foremost, the program chair, Corina Passarano. Next, the organizing chair, Miloš Gligoric. Sorry, previous slide. The publicity and virtualization chair, Jonathan Bell. The workshop co-chairs, Oksana Tachuk and Lin-Min Zhong. The artifact evaluation co-chairs, Rodi Kirsten and Casper Lukau. Professors Marcel Yu, Xin Hui Tan, and Mattia Fazzini. It was not afloat. Next. For the main conference members who participated in a top quality reviewing process that allowed us to have an exceptionally high quality program. Corina will give more details on that a bit later. Next.
Safaz, I don't know if it's just me, but I cannot hear you.
I would next to
Corina, maybe it would be better if you took over for this part while Sarfraz is troubleshooting his connection.
Okay, so I will continue because Sarfraz has a bit of trouble connecting, it seems. Is that okay? Hello?
We can't hear him, but just go ahead. That'd be great.
Yeah, okay. Please go ahead.
Okay, so we would like to, I will take over from Sarfraz because it seems he has a poor connection. So we would like to thank the student volunteers who has done a tremendous job already in helping us with running this conference online. And you have them listed on the slide, and you'll also see them their names during the conference. And we are very pleased to announce that we have a keynote by Barbara Liskov on reflections on programming methodology. And this talk will be today in this session, starting at 9:30. Professor Liskov from MIT is one of the first women to receive a doctorate in computer science in the United States. She is a winner of the 2008 Turing Award for her work on programming language and system design related to data abstraction, fault tolerance, and distributed computing. And we are really excited to have her talk today. We also have an award session tomorrow at 9 a.m. We already listed the awards on the website, but we'll have a small ceremony tomorrow. So please join us for tomorrow. I'm also giving some details about the technical program and some statistics. So we had a total of 162 submissions, which apparently is a new record for ISSTA. From these high quality submissions, we selected 43 papers. And we had a double-blind reviewing process, and typically each paper received 3 reviews. In some cases, we asked for an extra review where we felt there was a lack of expertise. So EasyChair computed for us that we had in a total 479 reviews. And we also had a rebuttal process and also an artifact evaluation for the accepted papers. And I list here on the right-hand side the number of submissions and accepted papers per countries. And you can see we have had papers from all the continents and from many countries, United States being the first, not surprising since the conference was supposed to happen in Los Angeles in USA, but also China, Germany, Singapore, Canada, UK had very strong showings. And we have approximated 470 registrations, which apparently is also a record for a standalone ISSTA conference. And some information about the logistics for the conference. Our intention is to have an interactive event, but as you can see, this can be a bit difficult due to internet connections. So anyway, the technical talks will take 20 minutes. This is approximately 17 minutes for the presentation and then 3 minutes for question and answers. And we ask all the presenters to please contact the session chairs before your talk. Ideally, you should log on 15 minutes before your talk and connect with the session chairs and also with the student volunteers assigned to your session to make sure that everything runs smoothly. Questions will be posted on Slack and will be read by session chairs. In order to provide for poor connection or other technical difficulties, we also asked the authors to provide us videos for their presentations, and the student volunteers will play these videos in case of technical difficulties. But of course, we understand that the presenters put a lot of effort in the video, so if they just feel like playing the video, that's fine too. Just let the student volunteers and session chairs know, and the presenters and ideally all the authors should still be online for questions and answers. As already mentioned, we have an artifact evaluation track, and this is was led by Rodi Kirsten and Kasper Luko, and they received 20 submissions for artifact evaluations, and they provided 3 reviews per submission. They also had a committee who reviewed the received the artifact evaluated functional badge, and 9 received the artifact evaluated reusable badge. And they also gave 3 awards, and you will get information about that tomorrow in the award session. Furthermore, we have a tool demo track that was chaired by Olobi Legunsen and Ting Yu, and they received 27 submissions. Again, there were 3 reviews per submission. And from the 27 submissions, they accepted 9 tool demos. And we will have a tool demo session on Wednesday. We also had the Doctoral Symposium that already happened on July 18. The Doctoral Symposium chairs were Marcel Baum and Jaco Geldenhuis, and they had 5 submissions, 3 accepted, and 2 great invited talks. One was given by Claire Legouze and the other one by Munira Abano. And again, we also had a great summer school on the first day of the conference on Saturday. And we had 4 great invited speakers that covered testing. So we had Nadia Alshawan from Facebook talking about testing at Facebook. Then we had the joint talk with Doctoral Symposium given by Claire Legouze from CMU. And we had another lecture on debugging given by Alex Sorsa from Georgia Tech, and on security by Somesh Jha from Wisconsin. We also have 2 co-located workshops. One is the international workshop on smart contract analysis, and the other one is the workshop on testing, analysis, and verification of cyber physical systems and the Internet of Things. And the workshop chairs were Oksana Terchuk and Lingming Zhang. And finally, we would like to give our special thanks to Milos Gligoric, who was the organizing chair for the conference and who has done an amazing job coordinating with our amazing student volunteers and thinking of all the tiny details that make a virtual conference run smoothly. So we really want to thank Milos. He is great, and if you want to organize a conference in the future, please involve Milos. You will not regret it. I would also like to give our thanks to our sponsors. Of course, as you know, ISSTA is an ACM SIGSOFT event. And we received sponsorship from AWS, also from MOOCtest and Synopsys, and this allowed us to make the registrations free. And in this way, we were able to attract a lot of people to register. And I would like to now invite you to enjoy the conference. And we wish we were all in Los Angeles and we could see the Hollywood sign on the hills in LA, but for now, please enjoy this nice picture. So this would conclude our opening, and we'll now take a short break, and we will be back at 9:30 sharp for the invited talk by Barbara Liskov. Thank you.
Hey everyone, just an announcement. While we're waiting these 17 minutes before the keynote, if you are going to be hanging out at your computer, why don't you jump into a video chat in our virtual lobby to say hi to all of your fellow participants. Just join Slack and type /video to get started.
Thank you. Safras?
Hey, hi, yes.
Ah, okay. So do you still want to check that you can do the presentation and or how do you want to proceed if the connection?
Yeah, I checked before. I just try and I have a different connection now. So
you're muted now because this is still live streaming to YouTube. So let us know if you want to stop that.
Okay. But do we want to do a test with Barbara as well? Safras, you are muted.
okay. Yes, so we need to set up, so we can try that now. Okay, so it's about time. So we can get started. I hope you can hear me okay this time. So it is my great pleasure and honor to welcome Professor Barbara Liskov to give our keynote. Professor Liskov is an institute professor and head of the Programming Methodology Group. Her research interests lie in programming methodology, programming languages and systems, and distributed computing. Her major projects include the design and implementation of CLUE, the first language to support data abstraction, the design and implementation of Argus, the first high-level language to support implementation of distributed programs, and the Thor object-oriented database system, which provides transactional access to persistent, highly available objects in wide-scale distributed environments. Professor Liskov's current research interests include Byzantine fault-tolerant systems, peer-to-peer computing, and support for automatic deployment of software upgrades in large-scale distributed systems. Professor Liskov is a member of the National Academy of Engineering and a fellow of the American Academy of Arts and Sciences and the Association for Computing Machinery. She received the Society of Women Engineers Achievement Award in 1996 and the IEEE von Neumann Medal in 2004. At the ACM SIGPLAN Programming Languages Design and Implementation Conference in 2008, she was awarded the Programming Languages Achievement Award. In 2009, Professor Liskov received the Turing Award from ACM. For me, at a personal level, I feel truly fortunate to host Professor Liskov's keynote. She's one of the first professors I communicated with as a prospective student who had just got admitted to the MIT Computer Science PhD program and couldn't believe that was true. Professor Liskov's pioneering work on abstraction functions and representation invariants, commonly known as repo-K methods, provided a foundation for much of my career's work. Thank you, Professor Liskov. Welcome to ISSTA. The floor is yours.
Thank you very much for that kind introduction. To prepare for today's talk, I started thinking about programming methodology and what it was like when I started working on it and what I think of it now. So that's what I'm going to talk about today. Next slide, please. I got into programming methodology in 1970. I got my PhD at Stanford in 1968. I did my work in AI working with John McCarthy. And when I went to look for a job, I couldn't find any good jobs as a professor. And so I accepted a research position at the MITRE Corporation. I had worked at MITRE previously between my bachelor's and my PhD programs. And so I went to MITRE, and this actually turned out to be a really good decision, a kind of blessing in disguise, because I was switching out of AI into systems. And that's a pretty big transition. And that way, being at MITRE, I had plenty of time to make this transition without being distracted by the need to teach courses and other stuff that you have to do as a professor. My first project there had to do with first computer architecture and then operating systems. And then in 1970, I was asked to look into what was called the software crisis. Now, many of you may not know what this is, but it was a big deal at the time. The problem was people didn't know how to build software systems. And it was not uncommon to pick up the newspaper and read a story about Company X that spent millions of dollars and hundreds of man years on trying to build some system. And in the end, they had to throw it out because it just didn't work. And this was true in the 60s, the 70s, right through the 80s. So people really had a problem building software. And MITRE mostly works for the military. And the military was concerned because they were building fairly sophisticated systems at that time. So I was asked to look into this. And this is how I got into programming methodology. Next slide, please. And I discovered that programming methodology was about two topics. One was how to design programs, and the other one was how to structure the programs that you're aiming for. Now, what I'm going to do next is I'm going to talk about a few of the papers that I read at that time. There were several really good papers. Of course, I did what you're supposed to. You're supposed to read the papers. And I've revisited them when I got the Turing Award, and they're very interesting. The first one I want to talk about, next slide, is the paper by Edgar Dijkstra, Goto Statement Considered Harmful. I hope all of you have read this. It's not actually a paper. It's just a letter to the editors of the communications of the ACM. And what Dijkstra is pointing out in this paper is that software is actually a difficult intellectual activity, building programs that work. And it would be a good idea to avoid using program structures that got in your way. And the Goto was such a program structure. And the way to understand his argument is to think about debugging. When you find an error in your code, you're at some particular point in your code and you have to understand how you got there. And it's relatively easy to do this if you use well-structured control structures like ifs and whiles and procedure calls. But if there are go-tos, it's a terrible mess. And people used to talk about bowls of spaghetti. So Dijkstra was pointing out the go-to statement wasn't such a great idea. This was a very controversial paper. A lot of people were insulted because they said, I build very nice programs using go-tos, and they felt that Dijkstra was attacking them. And they were absolutely right. Not that Dijkstra was attacking them, but that they could build very good structures, good programs with go-tos in them, because you can build a good program in any programming language, no matter how terrible it is, if you're well-disciplined. The other argument had to do with the state of the art in programming languages. People were really concerned about whether the loss of the Goto statement would mean they simply couldn't write the programs that they needed to write. And this stemmed from the fact that the control structures available in those days were not what we have today. Next slide, please. The next paper is one by Nicholas Weert. This is about design, and Weert is talking about top-down design, which really all design has to be top-down design, because if you don't pay attention to what you're trying to build, you're never going to get there. His idea in this paper was that you are working on the design of some module, you make a single design decision, figure out a kind of a program structure that fits that at a top level. So you just write down a little bit list of comments about, first I do this, then I do that, then I do this. And after you're convinced that you're on the right track, then you select some of those statements and look at them and figure out what they mean. And the example he used was the 8 queens problem. The decision he made was to proceed column-wise. So at any moment in time, you're at a point where you have put queens on the first n columns, and now you're going to move on to column n+1. And so you see if you can position a queen on that column that will fit with all the ones you have on already. If you can, then you move on again. If you can't, you backtrack. So that was his idea. Of course, top-down design isn't quite so straightforward as this. We all know that. Sometimes you get off on the wrong track, you have to backtrack, and so forth. Next slide. The final paper I want to talk is about by Dave Parnas. And this is now a program on modularity. Dave wrote 2 papers at this time. And in the other one, the one I didn't reference here, he said, we all know we need something called modules, but we don't know what modules are. And that was a very telling statement about the state of the art at the time. This paper talked about connections between modules, and this is a quote from the paper: the connections between modules are the assumptions which the modules make about each other. And you can see that what Dave is getting at here is the need for specifications and the fact that the specifications have to be complete. And to really understand this statement, you need to understand how programs were designed in those days. There were a lot of global variables, and there was a lot of communication through global. So it wasn't so simple that there was a procedure with a few arguments. It was sort of a mess in many cases. Okay, continue, please. Next slide, yeah. So the situation in those days was we sort of knew we wanted something called modularity, but as Dave said, we had no idea what it was. We did understand its benefits. We understood that with the right modularity, you could have independent development. That was very important at the time with those huge teams of programmers building that software that didn't work. It's important for local reasoning, because how can you possibly reason about the sizes of programs of the sizes that we deal with these days? And also important for modifiability, so that if you discover you need to re-implement part of the program, you don't have to worry about re-implementing the entire program. Okay, next, please. But the situation in 1970, we didn't understand modularity. Part of the problem was we only understood about procedures, and those were a very useful kind of module, but they're not nearly powerful enough for the kinds of stuff we were trying to build, like, say, a file system. They were used less than you might have thought. And the complications, they had these complicated connections, partly because of all the communication through globals. Okay, so I thought about those papers, a whole bunch of others I haven't told you about. And I realized that I had actually invented a design methodology in my work on the Venus system, the operating system that I developed at MITRE. So the thing that was, so I wrote that up and published a paper on it in 1972. As I said a minute ago, the way programs were organized in those days, there was a lot of global state and communication through global state. And this wasn't working all that well. So what I decided to do, if you can show the next slide, please, is to make a rule for the development of the implementation of this multi-programming system, that we would not have a global state that was shared by all the code in the system. Instead, I partitioned it into what I called partitions. So each partition owned some portion of the global state, and the rest of the code was unable to access that portion of the global state except by calling some operations that the partition made available to it. So you can see here, you know, you'd have a file system with some operations that the rest of the system could do to use files. You could have a device subsystem and so forth. And this worked very well for my team. So I wrote that up, and that was published in that paper I showed you a minute ago. Next slide, please. So at this point, it's now 1972, and I moved from MITRE to MIT. What happened was I had written a paper about Venus. It was a prize paper at SOSP in 1971. At that time, things had changed. And unlike when I got my PhD, where I feel that the universities had absolutely no interest in hiring women, things had changed a bit. Now Title IX was coming along, and some universities, or at least one, namely MIT, was interested in hiring women. So the chair of my session was Jerry Salzer. He was a professor at MIT, and Corby, Professor Fernando Corbato, was in the audience. And as a result of my paper and my talk, they invited me to apply to MIT, and so I moved. And it was a really good time for me to move. I was firmly into my new field. And not only that, but I had a problem that I was really passionate about. And so I came to MIT, and I was determined to work on priority methodology. And the thing that was consuming me at that point was this question of how can these ideas that I was reading about in these papers be applied to building programs? The trouble was you would read these papers, they would seem very reasonable. And so you would say, well, yeah, that's the right way to go about it. But then when you tried to apply the ideas to your own system, it kind of fell apart. And I was looking for a way to make it more real so that people could really use it. And sometime in the fall of 1972, or maybe very early in 1973, I all of a sudden saw that I could relate partitions to abstract data types. So I invented this idea of abstract data types. And if you go to the next slide, it's kind of, okay, next slide. It's kind of obvious if you look at that. I mean, look at that partition. It looks kind of like an object. It's got some hidden state. It's got a bunch of operations. Really, it's not an object. It's more like a data type. So it's the whole thing that, you know, controls the use of those objects. But nobody had seen this connection before. When I go back and look at the literature, you sort of see it floating around, but it just wasn't quite there yet. And I knew right away that this was a really important discovery because, first of all, data types are abstractions, and this is how you should design. You can't just design by looking for modules of size 100. You have to have some reason for figuring out that there's a module, and abstraction is the way to go. Secondly, programmers were already used to abstraction. They knew about procedures. They could invent new procedures. And furthermore, they understood data types. So inventing new data types was not going to be such a stretch for them. Plus, you could put it into a programming language, and then it would be there where they could use it. So I knew this was important, but of course, the question was, how does a programming language support this? Next slide. So I started to work with Steve Zillis, and what we were working on was trying to flesh this out, this sort of vague idea. Steve had a similar idea, and we were trying to flesh out this vague idea about data types and what this would mean to have a programming language in which data types were supported. And of course, what we did is we read the literature because we're moving into programming languages now. And I just want to talk about a couple of the papers we looked at. Oh, and I should say about Steve, since we went backwards, that he was a graduate student at MIT, but he was also an employee of IBM, and he was older and he had a lot of experience. And between the two of us, we knew quite a bit about programming languages. He was IBM. IBM was one of the major language developers at that time. And I knew Fortran, I knew Lisp because I'd done my thesis in Lisp. And of course, both of us knew a lot about the ALGOL languages, which were the big deal at the time, the ALGOL-like languages. Okay, next slide. So the next paper, this paper by Ole Johan Dahl and Tony Hoare is about Simula 67. So Simula 67, of course, was the basis for Smalltalk and that part of the object-oriented languages that's with us today. We looked at this, and you could see that a class with its methods inside was kind of what we were looking for, but there was a lot of stuff that we weren't looking for. First of all, there was no encapsulation. Secondly, the business of having subclasses seemed not that important to what we were trying to accomplish. So we put that aside. The second paper I want to talk about, the next slide, please, is a paper by Jim Morris. And what Jim was doing here was he was trying to put some teeth into the notion of what a module ought to be, or what does it mean to support modularity. And what he's interested in particular is how can you reason independently about modules? So what he said in this paper is he said, first of all, the code on the outside of the module better not modify any internals of the module. And this is, clear, because if it could, then you obviously can't reason independently, because after all, you have no control over what's going on. The second thing he pointed out is you really ought not to read the internals either. And that reading doesn't interfere with separate independent reasoning, but it sure interferes with a good modifiability structure where you'd like to rip the module out and replace it with a better implementation. But unfortunately, the rest of the code depends on how it was implemented before. Then Jim went on to talk about how could a programming language possibly support this? And this was the mystery that we were aiming at. And he proposed something like encryption. So the idea is that the code implementing the module has a secret key. Everything that goes out is encrypted. Since the code outside doesn't know the key, it can't muck around. So that last part clearly wasn't going to fly as a technique because it was much too expensive. But it was a very important paper nevertheless. Next slide, please. So Steve and I worked on this right through the summer of 1973. And my recollection of the summer of 1963 was that it was sunny every day in Cambridge, Massachusetts, because Steve and I had a routine. We would meet for lunch every day in the courtyard outside if we could. Of course, it wasn't sunny every day in Cambridge, Massachusetts. And we would discuss where we were, and then we would separate and go separately and think about stuff and come back the next day. This turned out to be quite effective because by the end of that summer, we had fleshed out our ideas and we submitted this paper to the Conference on Very High Level Languages. This gives you an idea, by the way, of what the programming language field was like then too. The conferences we're familiar with weren't necessarily there at that time. Okay, so now it's the fall of this is what it proposed, a fairly modern view of what abstract data types are. Namely, they have objects, the objects have operations, and the operations are how you interact with the objects. There was also a sketch of a programming language. Okay, next, please. So now it's the fall of 1973, and I'm taking the obvious next step, which is to actually design this programming language. And this I did primarily with 3 students, Russ Atkinson, Craig Shafford, and Alan Snyder. They were all first-year students who came to work with me at that time. Steve was watching and he was participating, but he was focused on his PhD thesis, which was about algebraic specifications for data types. Okay, next slide, please. So the rationale for doing the programming language is really obvious. First of all, a programming language is a mathematical entity. And so in order to have a programming language that supported data abstraction, we're going to have to be precise and have techniques that really were well defined. And I felt that, in fact, part of the problem with all these papers that I'd been reading was that there was a lot of hand waving and nothing very precise. And without something precise, you haven't got much to hang on to. So this way, we wouldn't have to really come to grips with what were the rules, how did you implement data types, what else was needed, and so forth. The second point was that a programming language has to be easy to use. It has to do what you need. It has to be convenient. You have to actually build code in it. And this was very important because it really wasn't clear at that point whether data abstraction as a technique was going to really fly. So this needed to be proved. And then in addition, performance matters. I do think people pay too much attention to performance, but nevertheless, you need good enough performance. And if it turned out that you could build lovely programs, but they perform so poorly you wouldn't want to use it, that was also an issue. So it was very important to do the design. Next slide, please. There were a few things I decided early on in the design of Clue, and a lot of this stuff just has to do with Lisp. I mean, I realize that now. So I insisted on static type checking. In a way, that's clear anyway. If you're working with data types, this is going to be how we're going to define, what's implementing a type, what's not implementing a type, who can get where, and so forth. But this also had to do with the reaction to Lisp, because when I was working on my thesis, it would be so annoying to spend a lot of time finding what the problem was, what an error was due to, and discover that if there'd just been a type checker, I wouldn't have had that problem. The next 2 things are also coming from Lisp. It may surprise you to know, but separate compilation wasn't much of a thing in those days. It wasn't uncommon for entire programs to be compiled at once. But Lisp was different. You kept adding new procedures to the language. And then, of course, Lisp was heap-based. And maybe it will surprise you to know that pointers were considered evil in the mainstream programming world. And but Lisp, used them. And it turned out that it was actually a very important decision that I decided to be heap-based, because one of the things about data abstraction is that you'd like to be able to use programs, have programs that use objects of the data type, maybe even implement them before the real objects exist, or you might have little simulation objects that you're using. And when you get around to the real implementation, the real objects might be of a different size. And this is a complete non-entity, non-issue if you're a heap-based language. But if you're a stack-based language, it's a big deal. And the Alphard project that was done by Bill Wolf and Mary Shaw at CMU, which was the other very early programming language to investigate data abstraction, was a stack-based language. And this caused them a lot of problems and slowed down their design. They had to work out how to make this work. The final point is no concurrency, because that was going to be a distraction. No Gotos, because I believe what Dijkstra said, and no inheritance, again, because it would have been a distraction. Okay, next slide. I'm not going to tell you much about Clue. I just want to point out that it took most of the 70s to design it, so quite a bit of time. Partly this is because programming languages are hard to design. But another reason for it was that we had to innovate in many different ways. So for example, exception handling was not then what it is now. There was very little in the way of programming language support for it. And so we had to sort of deal with that. We needed iteration mechanisms. Of course, we needed a mechanism to implement the data types themselves. In a way, though, I think the most interesting one there is polymorphism, generics. There wasn't polymorphism in those days. You didn't write procedures that could be parameterized to work on type A and then later run on type B and so forth. And actually, if you think about it, before there were abstract data types, there wasn't that much motivation for polymorphism because there were just a few built-in types. But as soon as you have data abstraction, you know you're going to have polymorphism, because you cannot just keep re-implementing things every time somebody comes up with a new type. So this was a hard one, and we came up with a mechanism somewhat like Haskell classes. And anyway, that's basically what I wanted to say about Clue. So next slide, please. So now it's sometime in the late 70s, and Clue is finished, and it has a nice compiler, and it has a user base, and they've written some substantial programs, and they're very happy with it. And I'm looking for the next thing to do. And I decided not to pursue programming languages, at least not Clue or mainstream languages. And I also decided that I wasn't interested in commercialization, which would have been a very different matter in those days than it is now, because it would have required a company and so forth. And I was a researcher. And I was sort of looking around, and I read a paper by Vint Cerf and Bob Kahn about distributed computing. They were talking about the DARPANET. And one of the things this paper said was that they had this dream of distributed programs that ran on different computers connected by a network, but they didn't know how to build those programs. And I thought, that's a great area for my next research project, which was the Argus language, where I could put modules and objects at different places in the internet. So I moved into distributed computing. I did a lot of work, including the work on Byzantine fault tolerance, which has found its killer app in the blockchain world. But in addition, I was still interested, if you can move to the next slide, in programming methodology. And I continued to work in programming methodology through the 80s into the 90s. But mostly this was done in the context of teaching. So I was asked in the late 70s to develop a course at MIT. This was the second course in programming. So the idea was the students knew how to build small programs, and this course was going to tell them how to build big programs. And I was working jointly with John Guttag, not in the very beginning, but shortly thereafter. And so we developed this course, which, it being MIT, doesn't have a name. It just has a number, 6170. And we wrote 2 books about this. The first one, Abstraction and Specification in Program Design, was about the version of 6170 that used Clue as the programming language. And then later in the 90s, when Java came along, I moved the course to Java and there was a second book. Next slide, please. So here's what that course was about. It was about modularity. So modularity is the key to building big programs. And so I was teaching the students about modularity and all the stuff that goes with it. And one of the things I was addressing was the question of how do you get there? You want modules, how do you find them? Next slide, please. And what I did was I proposed a design methodology, which is like what Veert was talking about, top down, but different, because now I had data types that I could use. And so the way I taught it, I said, here you are, you have some module, you know what it's supposed to do, and you're trying to figure out, how to accomplish this. And you don't want to write a lot of code in one module. What you want to do is you want to find other modules that do most of the work. And then this module will just use them. And the way you do that is you invent an abstract machine. So, we had machines, they had instructions, they had data types, integers, and so forth. So very similar idea. It's just that now, the sky's the limit. I can have any data type I invent. The instructions are obviously procedures. And so now I have this very nice machine. If it existed, I'd be done. But of course it doesn't, and so I have to iterate. And a simple example that I just sort of came up with is if you think about an online shopping system, at the very top level, you would understand that you had various things you had to accomplish, like browsing, ordering, delivery, and you'd have a bunch of data types that would be used by these sort of major subsystems to communicate. And by the way, the data types are really important here because that's what keeps you, you're safe from this big global data problem that otherwise pervades things. Next slide. So that's great. And you can see that, once you've figured out that your top level is fine, you can say, well, here's an abstraction. Let's go figure out how to implement it. But the trouble is, this only works if you know what that abstraction is supposed to do. And abstractions are ephemeral. You have to describe them, and you describe them by using specifications. At the very top level, these specifications might be incomplete because you don't understand fully everything about the abstraction, and they certainly don't need to be formal, but they definitely need to be there. So specifications are critical. So abstractions are critical, specifications are critical. Next slide, please. So there we are, modularity. Each module has an interface. It actually corresponds to the implementation of an abstraction, and the interface is described by a specification. So once you have this, you're really in business. Now you can have independent development and so forth. And what's really important is that you get a very nice independent reasoning process. Next slide. So now you can say what it means for a module's implementation to be correct. It's correct if it meets its specification, and you can even prove it by reasoning about the code of the module. That module might use other modules, but that's okay. You've got their specifications, and so you can reason using those specifications. And there used to be arguments about this. People would say, oh, specifications are complicated. Why is it better to use the specification than the module code itself? Well, specifications are declarative, and they don't contain information in them about exactly the details of how you solve the problem. So they are, in fact, simpler than modules. And by the way, as I said before, they can be informal. But the other point is that that module you're using, if you looked inside it, you might discover it's using other modules. But at this level, I don't care at all. So a huge complexity gets hidden by the fact that you can deal with the module via its specification. So this is sort of modern stuff. And what I like about it is that the proof of a whole system is like the proof of a theorem. You start off with a little proof of the top level module that it meets the requirement spec. And then you just pick up the modules one by one, doing this over and over. Each one is independent. It's lovely. Next slide, please. Next slide, please. Oh, okay. But yes, there is one issue that we haven't tackled, and that's encapsulation. Because programs, of course, are not mathematical theorems, and they can change state. And if code outside a module can change its state, the whole thing falls apart. And furthermore, if the code outside the module even reads the state, This is not so disastrous, but it does mean that you've lost modifiability. So we really need encapsulation, and it's appalling, honestly, that all programming languages don't support this. Next slide, please. So there we are. This is modern modularity. It's based on abstraction. It requires specifications and encapsulation. And once we have that, not only we do get these independent development, modular reasoning, modular re-implementation, but also specifications give us a great basis for testing methodology. But sometimes modules are related. Okay, so now I'm going to talk about what happened in the mid-1980s. Next slide, please. I was asked to give, I wasn't thinking about inheritance. I was asked to give a talk at ISSTA. I believe this was going to be the second ISSTA, which gives you a sense of what programming languages conferences were like that time. And I decided this was a good time to look into Smalltalk. And not just Smalltalk, but a whole bunch of other Smalltalk influenced languages that were being developed. And this work was primarily happening on the West Coast, whereas the data abstraction work was happening on the East Coast. And there wasn't much communication between these two communities, which was an odd thing, but had to do with air travel wasn't quite what it did today, and the conferences weren't quite there yet, and so forth. So I started looking into Smalltalk and other languages. Next slide, please. And of course, inheritance is used for implementation, just like it was in Simula 67, but it was being used for something else, type hierarchy, which I thought was really interesting. And it was clear from reading the papers that people didn't understand what it was. Next slide. Because I remember well reading a paper that talked about stacks and queues, and it said stacks are subtypes of queues are subtypes of stacks. And clearly this is not true, because their behavior is quite different. And if I wrote a program that expected a stack and it got a queue instead, it might not work correctly. Next slide. So I thought about this and I came up with a definition of what subtypes should be. And I presented this in the keynote at ISSTA in, I think it was 1987. And what I said fundamentally was that objects of subtypes should behave like those of supertypes if used via supertype methods. You know, this is, I'm being very careful here. I only talk about supertype methods, so I'm not precluding other methods. And I'm talking about behavior. I didn't talk much about specification in this part of the paper. I don't remember what I did in the talk, but I intended this to be behavior all along. This came to be called the Liskov substitution principle. I did not invent that name. I knew nothing about what was going on with this until sometime in the early 90s when I got an email from someone saying, can you tell me if this is the correct interpretation of the Liskov substitution principle? Next slide, please. So at about this time, Jeanette Wing approached me and said, you know, we really ought to define more precisely what behavioral subtyping is all about. You know, what I had was a very intuitive notion, but going from there to the rules and what the rules were that should be enforced is another step. And so we began to work on this together. We published a couple of papers on this. Next slide, please. Well, as I said, it's a property of specification. And very importantly, it does not prevent a subtype from having more. It can have more methods, more behavior. It's not something a compiler can enforce. It has to do with meaning, good use for program verification. But of course, lots of things are good use of program verification. Next slide. Okay, so the rules that we came up with, I'm going to describe briefly. The obvious one is the method rule. The subtype has to provide the supertype methods with the correct signatures. And of course, the compiler can enforce this much of it, but also the right behavior. It can have a weaker precondition because all we require is that any call that the using code could legally make is going to be okay. And it can have a stronger postcondition because all we require is that whatever postcondition we're relying on is still there. Next, please. But it's not the whole story. The thing is that data types have properties that can be proved from their specifications. And the using code has the right to depend on those properties. And the first kind of property you can depend on, you want to be able to depend on is what are called invariants. These are properties that are true of every object of the type all the time. So for example, if you're talking about a bounded collection, then you will be able to assume that anytime I look at an object, the number of elements in that collection is going to be less than or equal to the bound. Next slide. The other kind of property is what's called a history property. And these are properties that are true of every object of the type as it's used over time. So for example, if I have a collection where I can add elements but not remove any, then I'm able to rely on the fact that for some object X, all the elements that were there in state 1 will be there in state 2 for any state S2 that is later than state 1. Okay, so we know that the code of any program that's using the supertype gets to rely on these properties. Next slide, please. Next slide. Next slide, please. But the question is, how do you rely on them? And it was easy in the days when there were no subtypes because you had the specification of the type, and that was all you needed. You could deduce these properties from the specification. But the problem is these deductions are over sequences of calls. And what I'm showing you here is you start up an object with a constructor call, and then over time you call method, 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 method. I'm not giving any details of which methods these are, what the arguments and so on. It's just that every object has a history that looks like this. Okay, now next slide, please. If you think about what's going on when there are subtypes, what you see is, first of all the calls are going to the subtype. Okay, but we took care of the methods that are like the supertype methods already because we constrained them. So what I'm showing you here in red is the constructor, which clearly didn't come from the supertype, and the 2 red M's, these didn't come from the supertype, the 4 black M's did. And so how are we going to get these properties when we have no idea what these histories are going to look like? We want to allow those histories to be different because we clearly don't want to constrain the constructors of the subtype, and we wanted to have extra methods. Next slide, please. So our solution in some sense is obvious. We extended specifications so they state the invariants and history properties explicitly. And then we required that the subtype must support the supertype properties. Now it may seem, the history properties might seem a little strange to you because they have to do with code using the supertype, observing behavior that's caused by calls to subtype methods that aren't in the supertype. And it's true that in many programs, this is not going to be a problem. But if you think about a parallel program where in thread 1, I'm using a big object as if it belonged to the supertype, and in thread 2, I actually know it belongs to a subtype, and so I'm using all those additional calls, then you can see why you have to put the whole history thing together. Next slide, please. So I'm getting close to the end here. I just want to finish up by talking about what I've said. I've said everything. Modularity is what matters. Modules are related to abstractions. Each module implements an abstraction. Abstraction is the key to design. Abstractions have no meaning without specifications, and you need encapsulation to make the whole thing work. And if you get that whole thing together, now we have a really good way of building programs. Next slide, please. And I'm just going to conclude with this little story. So when I got the Turing Award, my husband was online every day looking at the comments. And not all the comments were nice because it's the internet, but some were. But this was one of the comments that I thought was particularly interesting. What this person said is, why did she get the award? Everybody knows this anyway. And I thought this was a huge tribute, actually, because yes, everybody knows it now, but it wasn't that way when I started that work. And the work of my work and the work of others has led to where we are today, where in fact, we don't pick up the newspaper and read about a system that failed. Thank you, that's the end. Next slide, please.
Thank you, Professor Liskov. So we can now take some questions. So for the listeners, attendees, if you can please post your questions either on Slack or in this Zoom chat. And just to get started, perhaps maybe I can ask one. So Professor Liskov, maybe you can comment on how do we convince developers to start using specifications more? Sometimes you see them in the form of assertions. So, and those tend to be very useful when they are there. But there is still this, like, in the real software development world, somewhat of a reluctance to rely on specs. I mean, people start writing code much more directly. So do you have some insights on how we can convince them of the usefulness of specs?
Probably I don't have any insights. I mean, I did use the word informal several times because I don't think you're going to have much luck trying to convince them to use formal specs. And actually, you get a huge amount of mileage out of informal specs. I don't know. I don't understand why this isn't being taught. I mean, it seems like, well, I can't really say that. I don't know. I mean, I think another problem is they go to implementation much too fast. And sometimes they like to specify by implementing as opposed to specifying and then implementing.
Right.
Yeah, and
okay.
Maybe you have to clean up after the fact because in the heat of the battle, so much is going on that, so I don't have an answer.
Right. Okay, there are some questions on Slack now. So one is by Marcelo Damorim. What is the best way to apply your ideas these days, especially given the tendency of implementing a little and reusing lots of components?
Well, actually, if you have a nice program library available to you, then this makes your job better, easier, because there's more available to work with. When I started this work, all you had as a programming language was something with arrays, integers, reals, strings, and Booleans. Now you have a programming library, and you don't have to implement a bunch of data types because a lot of them are all available for you. I think you might be talking more about picking up somebody's module that almost does what you want. I'm not sure what you're talking about, but that might be what it is. You sort of try to take some code that already exists and start changing it.
Right.
Might work. Yeah, but it seems a little ill-fated. There's no
question.
Yeah, go ahead.
Another question is from Corina Passerano. Can you please tell us about the programming languages influenced by Clue?
Can I tell you about the languages influenced by Clue? Is that the question?
Yes.
Well, I paid very little attention to this. But clearly what happened was that there were two parts to the object-oriented story. One part was the Smalltalk part coming from Simula 67. The other start was the Clue Alphard part, the data abstraction part. You have to put the two of them together because you need to have this notion of abstract data types and data types that are related to other data types. And so in a way, Ada was influenced, Java was influenced, C# was influenced, but I think it's gotten, so far into the, this is how we do things, and it's kind of ubiquitous. And teasing out, what came from Smalltalk and what came from Clue, both sides were important.
Right. Another question I have is while specifications are conceptually simpler than implementations, oftentimes, even though they are declarative in nature and implementations are more imperative, getting the specs can also be somewhat hard, getting them right. And sometimes it can be as hard as getting the code right. So in practice, would there be some insights that you may have on how we can reduce this cost, where perhaps we are first developing the specs, and then to get them right, we have to perhaps pay a fair amount. And then once we have confidence in the specs, then we develop the implementations. perhaps like, once you have a strong specification, we'll have a better implementation and we'll save some cost over there. But do you see some way of sort of maybe co-developing specs and implementations where sort of like we together are building the system, where the specs are also being sort of refined based on perhaps what we learned from some feedback that we get from the implementation, and then we go back to the implementation and make that better, so that like, overall we sort of don't pay the cost of getting things right multiple times?
So one of the things that I didn't say, I might have said it, but I didn't make much of a point about it, is that when you do design, those initial modules that you define are usually very ill-defined. So this, and one of the important messages, you don't want to start implementing too early, because you've got to keep going on with your design process. You don't really understand their specifications, because until you look more deeply into what's going on, you just don't know enough. And so it's important not to start implementing too early, because you don't want to waste time implementing stuff that turns out to not be useful, since I didn't understand enough about what the specification really was. So I think it is important to understand that specifications get developed incrementally as you go through the design process. As far as, I'm trying to think about, I think that maybe is the main message I have. And I mean, the other thing you get from, so I mean, another thing I didn't say, but this is probably not what you're talking about. So you talked about several things. So I'll say again, specs can be informal. It's much more difficult to write a formal spec. The next thing I said is specs are written incrementally. You don't want to try and write them. You don't want to write down more than you know. You might have to investigate the next step of the design before you fully understand, what's going on with this particular module. Another thing is that you organize your design by choosing the modules that are most specified and looking at them first, because as you look at them, the other modules, which they probably also use, will become more specified. I guess the final point is that I've always liked abstract model specifications. I actually think they're pretty easy to use, and there's a huge benefit in taking the time to say what they are, even if you write it down informally, because that way you understand the things you don't understand. So it really is a time saver. I mean, I think that people just don't understand enough about how much time you can save if you're just a little bit careful.
Right. Good point. So there's another question from Slack. It's by Darko Marinov. You discussed static typing. However, some of the most popular languages today are dynamically typed, for example, Python. Why is there a discrepancy between theoretically better languages and features versus practically more widely used languages and features?
Yeah, that's a good question. I don't work in the programming language world, but I did do some joint work with Andrew Myers in the last several years. And one of the things we talked about was this business of dynamic versus static typing. And I really think that this is something that could be solved with the right kind of programming language support. So I don't have any real complaint about somebody who's typing stuff in, avoiding typing those extra declarations. But I think it really is important to distinguish between the input form of a program and the real form of the program. The types become important as other people join the work, as things have to change later. And you really want to know what's going on. You'd really like the compiler to do it. So I think this dynamic stuff is more about making it easy to enter information. And it would be good if we had a compiler that could just sort of come up and help you with the stuff you don't feel like typing. Or at least by the time you're done, you have a program that really has this stuff all sorted out. The linear, the form of the program and its programming language has the whole thing figured out. I think that, there's been a long battle So you probably mostly don't remember APL, but I remember APL. And the idea there was you would write these one-liners, and this was considered just wonderful. You could write a program that did a whole bunch of stuff, and it only took a few characters. But the truth is that program readability matters much more than program writability. And so it'd be nice to find a way of having both. So that's my response.
Right. That's very good. Thank you. So I see there are no more questions on Slack or on Zoom. So perhaps we can thank you once again. Thank you so much for giving the ISSTA keynote. It really is an honor and pleasure for all of us. So thank you.
Well, thank you very much.
Thank you, Barbara.
Bye-bye.
Goodbye.
Bye-bye. Thank you. And for the attendees, we'll take a break, and the next session will start at 10:50.
Thank you.